Well, you mentioned, this important almost yin and yang between theory and experimental data.
Yeah.
And one of the most iconic places for that is at CERN, the Large Hadron Collider. Again, on your website, you talk about your current research is focused on maximizing the discovery potential of the Large Hadron Collider through new theoretical frameworks and novel data analysis techniques. So maybe just starting off for folks unfamiliar with the Large Hadron Collider, the LHC, could you just share more about its history and why it's such an important device?
Yeah, so the Large Hadron Collider is a 27-kilometer ring in Geneva, Switzerland, at a facility called CERN, which is really the focal point for particle physics research in Europe, but really worldwide. And the Large Hadron Collider is kind of a sequence of colliders leading up to it of ever-increasing intensity, that's the rate at which you're colliding particles, but then also increasing energy. And the Large Hadron Collider is the highest energy and the highest luminosity, that's the rate of collisions, collider that we have in current operations. The LHC started taking data in 2010. Famously, it discovered the Higgs boson in 2012, which was really a crowning achievement, the discovery of the last missing particle in the standard model of particle physics, and that's one of the reasons why the LHC is so important. And the subsequent running of the LHC after the Higgs boson discovery has been looking for cracks in the standard model to try to tell whether the interactions that we've already studied in the standard model, whether they might be augmented by additional particles, additional structures. And very carefully on my website, I talk about maximizing the discovery potential of the Large Hadron Collider, because I don't know what nature holds for us. It may be that, to the best of our knowledge and the best of our knowledge 10 years from now, it will just be the standard model of particle physics. Or there could be new physics lurking in the data somewhere, and new data analysis techniques are ways of taking the data from the LHC, processing it in different ways, and hopefully illuminating subtle features that might point us to new phenomena.
Okay. So you mentioned, the scale, the physical scale of the Large Hadron Collider. I went to a talk, actually I believe it was at IAIFI a couple of years ago, where they just talked about the sheer amount of data that comes out of these collisions. And it was in the form of petabytes, which is a word I hadn't even run across before. So, exabytes. Yeah, could you give us a sense of just how much data is generated and how much of it we're able to analyze?
Yeah, so one of the things about particle colliders which makes them different than other types of experiments is that it's a bit like the movie Groundhog's Day, where the same thing happens over and over and over and over and over again. And so every collision at the LHC is set up to be, to the best as we can do, identical. So the identical collision energy, the identical particles coming in, and then what you're looking for is quantum effects that will give you different quantum probabilities for different things happening. So something like production of a Higgs boson, that's very rare. And then there's other types of things that happen which are copiously produced. And we have to make decisions about what data is interesting and what data is less interesting, because the actual data rate at the LHC is mind-bogglingly large, such that even with the best computing infrastructure that we don't have the ability to write all that information to tape. And when I say to tape, I mean literally magnetic tape is actually used as one of the parts of the infrastructure at the LHC. So every 25 nanoseconds, particles collide. 25 nanoseconds. So 25 nanoseconds, that's roughly the amount of time you have to make a decision about whether that event is an interesting collision event that might hold evidence for new phenomena, or it's a boring collision event that might just be a garden variety type of collision at the LHC. And so you might imagine, of course, AI can be very useful if you're trying to make fast decisions. But each individual collision is not so big. Each individual collision roughly is the amount of data that you would have in a kind of 10 megapixel camera image. So each image is not so large. But 40 megahertz, right, or every 25 nanoseconds, that's how much you're coming out. And you have to drop that down from 40 megahertz down to kind of hundreds of kilohertz in order to make it manageable to do for offline analysis. And so it's not an experiment in maybe the traditional way you think of it, an experiment where you get to change knobs and change conditions. Here, the conditions are always the same. The decision making is whether you keep data or you don't keep data. And that's a daunting challenge. And there's always the worry that keeps me up at night about whether we might be throwing out interesting physics because we don't have the right algorithms operating in real time to try to decide what collisions to keep.
So are there, runs that are scheduled over the course of a year, or kind of have the experiments been done, and right now we're sifting through existing data? How is that being approached?
Yeah, so it's a combination. So there is a plan over decades for when you run. So you try not to run during times when electricity costs are high. And there's actually two different modes of running. There's a mode of running where you're slamming together protons, and that's relevant for particle physics, but there's also a mode of running where you're slamming together lead nuclei, and that's relevant for nuclear physics. So roughly 1 month out of the year is spent on lead nuclear collisions. I think it's 8 or 9 months are spent on proton-proton collisions. Then there's time for repairs and things like that. And then there's longer stops that could take a year, 2 years, 3 years sometimes when you're doing major upgrades. But this is a multi-decade project, and there's a lot of negotiation about exactly when you're doing your runtime, because you want to collect as much data as you possibly can. But you should be thinking about continuous. When it's on, it's continuous collisions all the time, every 25 nanoseconds. But you also need to replenish the beam. And so there's a certain amount of running time where you've accelerated the beams up, you have them collide. As the collisions happen, the number of remaining protons decrease. At some point, you dump the beam, restart. So there's a very complicated dance to try to collect as much of data as you possibly can at these colliders.
Well, you mentioned the Higgs boson and the standard model of particle physics. One of the sort of things I've heard anecdotally from physicists is that model is stubbornly accurate. And as you said, I think we're trying to find cracks within that model. There's also, some other folks who say, well, maybe that's just all that we can get to with this amount of energy that we're able to throw at these particles and to accelerate them with. And so maybe the unlock is going to be in the next generation of particle accelerators. So yeah, could you share more about how you think about that? Clearly, I mean, the benefit of the work that you're doing, and I want to get more into the AI aspect soon, is that the there might be there already, and there's a whole universe of work to be done in order to uncover maybe the signal within the noise. Right. Certainly also seems a lot more cost effective relative to building a big new facility. Yeah. But yeah, how do you think about sort of some of those perspectives on the state of new discovery? Yeah,
so actually, it's a complicated thing to negotiate. And in fact, before the Large Hadron Collider, there was a previous accelerator that was actually in the identical tunnel, the Large Electron-Positron Collider. And before it was decommissioned, there was actually potential evidence for the Higgs boson lurking in that data. And it was an incredibly challenging decision to say, you know what, we're going to decommission that particular accelerator and build a higher energy collider, the Large Hadron Collider. And once you gutted the tunnel, you couldn't go back. And so that's a complicated negotiation to say, should we continue to collect data at the current machine? Or do you actually go and build a higher energy or a higher luminosity machine to try to get a different type of data? And that is what our field is wrestling with right now, or has been wrestling with. And we've made collectively a decision that we are going to launch the high luminosity upgrade of the Large Hadron Collider. And that upgrade had a very particular target in mind, that given all the various technologies available, one of the things that we'd really like to understand is understand a particular property of the Higgs boson, which I'll describe in a moment. And it was decided as a community that the best way to get access to that information was indeed to run the LHC, but in this higher luminosity mode, collect more data, roughly spend another decade collecting data, and that would be the best chance for us to understand this particular property of the Higgs boson. But it's a complicated decision, because when you're doing that, that means that you can't do something else. And so again, it's a collective decision of the community through a lot of strategic planning to make that decision. But the reason why this particular property of the Higgs boson was so important was that we know that the Higgs boson is responsible for giving elementary particles their mass. And the degree to which the Higgs boson talks to various particles, that's proportional to how much mass they have. So the heaviest particle in the standard model is the top quark, and the top quark also has the strongest interactions with the Higgs. And we've measured the interactions of the Higgs boson with top quarks, with W bosons, Z bosons, but we've never measured the interaction of the Higgs boson with itself, because the Higgs boson itself has mass, and therefore the Higgs should in some sense give itself mass. And that was the scientific target that was used to decide basically how much running to do. And there's other science you can do besides that really big ticket item, but that was the thing that drove the decision for roughly the next decade of running in this mode of continuing the LHC. And now the decision is, well, what do we do after the LHC? What's the next collider that we build? And we're part of a strategic planning exercise. There's a version of it that happened in the United States that's called the SNOMAS process. And I served on the panel called the Particle Physics Project Prioritization Panel that made recommendations to the US government about how to prioritize activities in the US side of particle physics. Now there's a European strategy group that's meeting to try to decide things on the European side. And they are deciding, in some sense, what is the next accelerator that you would build after the LHC. And we're having these conversations of the trade-offs of different technologies, different timeframes, what is the science that we want to uncover. And those are really fun conversations to be had. And hopefully we'll come to a community consensus about what the best path forward is.
Well, one thing that I find so, I would say, heartwarming, and I'm sure it's different maybe when you're actually at those conversations, but from the outside, when I think about just grand projects that we take across nations, today, the LHC really stands out as one that is, financed, as I understand it, for multiple nations, involves scientists from all over the world, and by virtue of the fact that you can only create one of these or so many of these, you need to engage in this collective decision making with real tangible outputs and impacts on science and so forth. So I guess what can we learn from that process that from the outside seems like an inspired one?
Well, the particle physicists have had to do this out of necessity. Not everyone can have their own accelerator. There was a time when everyone really could have their own accelerator, and different universities would have their own private accelerator complex. But as you're going to higher collision energies and higher collision rates, you end up getting it to be cost prohibitive. And so the community, out of necessity, had to work collectively. And examples where we didn't work as collectively and where we maybe didn't get consensus of the community as a whole, those have been situations where particle physics hasn't done as well. And we've done our best science and engaged, the most science has also engaged society at large most effectively when we've done these big community efforts where there are multiple different science outcomes that come from the same machine. And so the LHC is not really just one experiment. It's many, many, many different PhD theses that are generated from the LHC. And so you're really trying to build an apparatus that can serve a huge range of needs of the whole community. In terms of the lessons that we can learn elsewhere, is that really in this era of big data and big science, which seems to be necessary to push the frontiers of knowledge, you really do need to have that community thinking. And the conversations that are happening now in the world of AI are ones that also drive us in that direction. That if we really want to see, coming from the academic side, great advances happening in AI, we may also need to do that kind of collective action and think about building AI models that are actually community efforts as opposed to small author list work, which is more typical in this area. But particle physics offers a very interesting case of, out of necessity, having people get on the same page and make collective decisions.